let's calculate this infinite sum from 1 to infinity. -1 to power n minus 1, log n over n. So it's essentially the first term would be positive. All right, log 1, right, which is 0, minus second term negative, minus half of log 2, plus third of log 3, right, minus log 4 over 4, plus log 5 over 5. I'm looking at this finite sum. All right. Finite sum. I'm going to stop at minus log 2n over 2n. Right. The all term, as long as the denominator is even, then it's always negative. Right? Previous term has to be positive. Right? As long as the denominator is even, denominator is odd, it has to be positive. So maybe plus log 2n minus 1 over 2n minus 1. Right? So this is finite sum s sub 2n. So that I'm going to group all the positive terms together. Log 1 plus log 3 over 3 plus log 5 over 5 up to log 2n minus 1 over 2n minus 1. The positive terms. Also the negative terms. Minus half of log 2 plus log 4 over 4 plus all the way up to log 2n over 2n. Now to make up this positive term, I have to insert some terms in here. Insert log 1 plus half of log 2. I also insert log 4 over 4. Right, just to make it complete. Right. Plus all the way log 2n minus 1 over 2n minus 1, and plus another log 2n over 2n. Right. Of course, I'm going to have to minus this term, minus this term. Right. Also minus this term. So, but I have exactly the same term in here. All right. So I'm going to add a 2 in front here, right? Minus twice of this sum. So minus twice of this. Log 2 over 2 plus log 4 over 4 plus all the way log 2n over 2n. Now, this is what, right? This is, maybe I can just factor out 2 out in here, right? Every denominator is even. Factor out half. Right? Then I can rewrite log 2n into log 2 times log n. Right? I'm going to also rewrite this into just a sum. Right? So this first sum k goes from k goes from 1 to 2n, right? Log k over k, right? That's this sum. Like I said, this sum I'm gonna first factor out half, right, from each of the terms, right? Half. Cancel out with this 2, right? So I'm gonna minus log again, minus log 2 times 1, right, over 1. Plus log 2 times 2 over 2. Plus, just one more term, log 2 times 3, right, 6. Right, 2 times. Previous it was 6, right, now it's 3. And the pattern is clear all the way. Now I have n, right? Half is already factored out. Log 2 times n. Right? Now I can just log 2 times 3, log 2 plus log 3. Log 2 plus log n, I can just separate them. This time I should have this time k goes from 1 to 2n log k over k. Right, this part becomes log 2. First I have log 2 times log 2. Every fraction I have a log 2, right? Log 2 plus log 2, log 2 plus log 3. Log 2 factor out, and I have 1 over 1 plus this part 1 over 2, 1 over 3, right? 1 over 2, 3, 1 over n, and not only that, I still have. Remember, after I separate them, I have log 1 over 1, log 2 over 2, log 3 over 3, log 4 over 4, log n over n, right? So this time I still have log k over k. K goes from 1 to n. So this log n, right. Okay, I'm going to deal with this part later. And this part, right, they can just combine together. Right? Only difference is that I'm starting from 1 to 2n, but here I start from 1 to n, so the first n terms are exactly the same, right? All canceled out. So the only thing left is that I'm only left with k goes from n plus 1 up to 2n, right? Like I said, previous n terms are all gone. And log k over k. And minus log 2 times sigma. K goes from 1 to n of 1 over k. Right? This is what I have. And as for this part, right, this part, let me just write it as k goes from 1 to n. Right, I'm going to re-index it. Right, previously starting from n plus 1, right? This time, if I read from 1, it means I have to start n plus k, right? K equal to 1 becomes n plus 1, right? The same thing, I start from n plus 1, right? After I re-index. Log n plus k, same thing, right? The same sum as this sum. Minus this log 2 k from 1 to n, 1 over k. There is harmonic sum. Now, this part, I can just rewrite it into times 1 over n multiplied by n as well. Right? Right? Multiplied by n as well. Log n plus k. Right? K from 1 to... Now, this part, n, right, n can simplify with the bottom. Right? N gone. I have n becomes 1. K over n this time. Right? So I want to turn this part into the same as this part, right? How can I do that? Maybe I can just factor out n, right? Divide by n as well. So 1 plus k over n. Right, same thing. Then I just separate the logarithm, right? Log of this part plus log of n. Right? Log n, right? 2 logs. Right. Then I can just separate this sum and this sum. Right? But log n has nothing to do with k, right? Log n is just a constant, can be taken out. Right? So this separated out. This time I should have log n taken out over n sum this part I want, right? Sigma from 1 to n. Right, 1 over 1 plus k over n, right? This one. The other part is this part over this. Still have 1 over n sigma from 1 to n 1 plus k over n log, same thing. Right? And of course, minus this part. Minus log 2 times 1 from n 1 over k. So far, I've reached this result, right? Our finite sum, right? The first sum, the other sum. Finally, we work out this sum. Then we will take n to infinity. Now this part, I can turn it into just n log n. So first it becomes n plus k over n, then flip it, right? K go from 1 to n. Right? N plus k, n plus k. This time at the bottom, n sits on the top, right after I flipped it. And so this time, n cancel out, right? They can just cancel. Now, this time, that part doesn't change. That part is a Riemann sum. I've turned it into a Riemann sum. That's my motivation. Okay. 1 plus k over n log 1 plus k over n. The same thing. Minus log 2 sum from 1 to n1 over k. And this part is easy. This part. This part, sigma 1 is in fact goes from 1, right? First term 1 over n plus 1, right? And 1 over n plus 2. All the way 1 over n plus n, that's 2n. Right? That is essentially, because remember, we've Tn, if Tn is this harmonic series, right, finite, right, then if T2n is this harmonic, right, up until 1 over 2n, right? Then we say, okay, this has to be their difference, right? So that is their difference. T2n minus Tn. Okay. But we also know that this is a famous equal log n, famous sum, well-known sum, plus Euler constant, gamma, plus big O of 1 over n. Right? So big O means just a bounded sequence, doesn't have to be unique. You can treat it as a bounded sequence as n approaches infinity, right? It's always bounded no matter what, regardless of the value of n. And that is equal to log 2n plus Euler constant plus big O of 1 over 2n. Right? But like I said, big O can be viewed as a bounded sequence, right? Some bounded sequence, it doesn't have to be unique, multiplied by this part. And so I can just simply get rid of the 2, right? Because it's just constant, 1 over 2 constant, multiply out, doesn't matter. Right? Big O of 1 over n, the same thing. So like I said, this time their difference, right, can be written as this minus that. Gamma, gone. Log 2n minus log n, log 2n over n, log 2. Right, log 2. Big O minus big O. Still big, they're not gone. Right? They don't just disappear. It still stays. Big O of 1 over n. Right? The reason is because, like I said, big O is not unique. Right? It is some bounded sequence, some other bounded sequence. Right? When you when you take their difference is still bounded. Right? Still bounded sequence, some other bounded sequence multiplied by 1 over n. So it still stays. So that way, I'm going to still work out, for example, this part, right? This part is also very simple. Right? This sigma 2, right? Sigma 2, like I said, sigma 2 is very simple. Using, right, log n plus gamma plus big O of 1 over n. Now I'm going to deal with this part. Right, this, perhaps I'm going to call it A sub n. Right? So A sub n is obviously Riemann sum, right? When you when you partition 0, 1 interval into n even intervals, right? And each small interval has the width of 1 over n, right? If we take the right edge, right, function value is taken at the right edge of each small interval, right? That's when you have a Riemann sign. So if we take the limit, that's the Riemann integral, right, from 0 to 1, whatever function it is. So the function should look like 1 plus x log 1 plus x, right? So the limit an is definite integral from 0 to 1, 1 plus x log 1 plus x dx. Right? The antiderivative, what's anti? So I'm assuming could it be log square 1 plus x, right? Because if you differentiate it, right, so 2 taken down, right, 2 taken down, maybe multiplied by half, right? 2 taken down in front, cancel out, and you still have log 1 plus x, but you still have to use chain rule, right? 1 over 1 plus x, right? The same thing. So it looks like that's the antiderivative. And evaluate it from 0 to 1. 0 to 1. Half of log square of 2, right? 0, log 1, 0, right, gone. So this limit. So sigma 1, sigma 1 multiplied by log n, right? Log n, sigma 1, minus log 2, sigma 2, right? That is equal to what? Sigma 1 equal to this, right? Log n, log 2, plus big O, 1 over n, right? Minus log 2, sigma 2 is that, log n plus gamma plus big O, 1 over n. That is essentially log n times log 2 plus big O. Big O of log n over n. And you can just multiply it inside the big O. So minus log 2 times log n, and you minus gamma log 2 minus log 2 times big O of 1 over n. Right? So essentially log 2 log n cancel out. And the log n over n, the n approaches positive infinity faster than log n. So this already approaches 0, multiplied by some bounded sequence. Of course, this thing will approach 0. Right? And also 1 over n approaches 0, right? Multiplied by big O, some bounded sequence, of course approaching 0, right? Multiplied by constant, still approaching 0. So this still stays. Right? That's a constant, Euler constant, right? Or constant. So that remains. And I still have this, right? That's the result I got from this limit, right? And also this part and this part together, eventually approaching this. Then I have this. So eventually I have eventually that's the result. Gamma log 2. Right? That's the final result.